Okay, so let's take a look at the post lab for titration curves. Um, all right, so we're going to start with the two discussion questions, and one and two. It does help to kind of actually draw out the titration curve, so that's what I'm going to do. So here we go. So titration curve of phosphoric acid. All right, so phosphoric acid is a polyprotic acid. You can do these calculations, but we can kind of uh, take a quick look at it. But H3PO4, this is going to have three H's kind of dissociate, meaning I am going to get three uh, equivalence points. Okay, so it's three titrations in one. So titration, you get the little plateau region followed by an equivalence point, and then you get another plateau region, and then another equivalence point. In this last one, you're barely ever going to see. It might just be a little blip, little blip. Most people will not see it, so don't feel bad if you didn't see it in your lab. It's kind of the typical thing to not see that. And you can kind of take a look on Google and take an idea or check it out and see what that looks like. So there was my first equivalence point VE. Let's see, undo that. There we go. So this is volume of equivalence one. That is expected to be volume of equivalence two. So there's one, there's two. This right here, this is volume of equivalence three. And these should all be the same volume apart. So if it's 10 mils to the first equivalence point, it should be 10 mils to the second, so on and so forth. So H3PO4, because we know what the acid is, we can actually look up the pKa. So pKa1 is 2.15. The This is going to occur at the halfway point between the equivalence and the equivalence point and the start of the titration. So it's the one half volume of equivalence. You're going to understand this much more when you go through buffers if you haven't already. But the reason that is true is because of how buffers work and the Henderson-Hasselbalch equation. There's a much quicker way to get to that. So hopefully you have buffers knowledge before taking a look at this. But if you don't, that's okay. We can still use those trusty ice tables. So the volume of equivalence this is the one half volume of equivalence. Keep in mind that's between, it's not from the equivalence point to the beginning. That one's between those two. And so we'll take a look at that. And then the other ones here, you're not going to see this one. This is the one half volume of equivalence three. You're not going to see that one generally. All right, so back to this. So pKa1 is 2.15. pKa2 is equal to 7.20. pKa3, which you are not going to see unless you're really lucky, 12.32. These are going expected to occur at these points. So this is expected to be 2.15, obviously not drawn super to scale because I didn't have time to perfectly make it. There we go. So now the question ultimately is, I don't really care about that. What I care about is figuring out what pH this occurs at. And so there's a couple of things here. Using indicator is significantly faster than using uh, a pH meter, which is fine. So I am trying to figure out when these are going to occur, and it's a lot easier to do it with an indicator. The good news is if I kind of zoom in here, the pH jumps a lot around this equivalence point, and because the pH jumps a lot, I just need to get a an indicator kind of somewhere in there. If I can get an indicator somewhere in there, then we are going to see that sharp curve pretty easily. So we kind of want to go in between 7 and 2.5 or 2.15. So I don't know, around 4.5 to 5. And I'm shooting for the second PK. So that one right there was it 2.15? Yeah, 2.15. Oh, sorry, that's not it. So yeah, we're shooting, this is 2.15. And then we're going to shoot in between 7 and 12. So that's probably around 9.5 to 10. That's where we're looking. So between 4 and 5 and 9.5 to 10. So let's take a look. So between for the first one between 4.5 and 5, I think we said. So somewhere kind of in here. Um, so here we go. So we can kind of toss out a couple of these, obviously. Um, this one looks like it is the Congo red, looks like it's purple for far too long. The bromocresol green or the methyl red. So I have sometimes it comes down to actually color as well, making a decision about what you actually kind of want to see in terms of, let me get this exactly upright. There we go. So we kind of have a choice between the methyl red and the bromocresol green. Um, we have a choice of choosing the transition we are looking for. Are we looking for yellow to emerald? Are we looking for dark red to orange? Our eyes are probably significantly better at picking up the change from yellow to emerald than they would be picking up red to orange. So I'm going to go with bromocresol green for that pKa1 value. That makes the most sense because that's going to be probably much more visible for us. And then the other one I said was between like 9.5 and 10, I think, right? 9.5 and 10. So yeah, 9.5 and 10. So we're going to go like here-ish. And so make sure this one's up right. There it is. And again, we have a choice between phenolphthalein and thymolphthalein. I am probably going to pick phenolphthalein because it is more present. And that's probably the best one, and that's going to be a pretty sharp curve, but you're totally fine doing thymolphthalein. I love these because they go from colorless to colored. Our eyes do a much better job of seeing no color to color than the other way around. So yeah, those are the two that I would probably pick for phosphoric acid. Sketch a titration curve for carbonic acid. Okay, so we're going to do carbonic acid. I would encourage you to kind of take a look at a handful of polyprotic acid titration curves. It's pretty interesting to see how varied they are. Phosphoric acid looks fantastic. You can see it, all three of them super stable. But if you look at carbonic acid, we see that the Ka values, we have two Ka values for my H2CO3, pKa1, which is 6.77, which is pretty high. So that's kind of where the first equivalence, not an equivalence point, but for plateau region, pKa2 is going to be 9.93. So this titration is going to shove two very small things in a very small range. So actually, it's going to kind of start with a very low pH. So this is volume of NaOH. So it's going to kind of start pretty low, and it's going to kind of jump up really quick right away. And then let's see, one, two. Oh, yeah, I got to finish it. There we go. Again, I would encourage you to kind of take a look at it. It's going to be interesting to see, but we have two equivalence points. One, two, they should be equidistant apart. So volume of equivalence one, volume of equivalence two. The pKa values, so we expect this to be at 6.77. We expect this other plateau region to be at 9.93-ish, give or take, halfway point. So you can label the axes and go from there. The volumes of, so if this happened at 10 mils, this has to happen at 20 mils. So that's what we should see. But yeah, I would take a look at some and kind of observe. They're kind of crazy. Carbonic acid, malonic acid, I believe, is another one that just kind of looks really funky. They either you get a quick peak or it takes forever to get that first one, but they're worth a look. All right. So moving on to problems. All right. So let's get at the information we got. A 2.68 gram sample of pure monoprotic acid. So we don't know what it is. We know that it is going to be HA. That's my generic acid, HA, dissolved in a little water, titrated with, okay, KOH, and requires 16.4 mils of KOH. Okay, so before we continue, I have my unknown acid combining with monoprotic, so just one proton, with KOH. So we always want to write out our equilibrium expression, or I'm sorry, or not our equilibrium expression, but our titration expression. That's going to make Ka, which is my conjugate base, plus water. So most important information out of this is it's a 1-to-1 ratio. Sure, every mole of OH that I use, it's the same amount of monoprotic acid. All right, so the information that I have so far is my mass of unknown acid is 0.2688 grams. My concentration of KOH is 0.08133 molar, and my volume of KOH is 16.40 milliliters. I'm just going to convert that now, 0.01640 liters, because I have a concentration, so it's going to be easier to convert to moles. There's plenty of ways to do it, but this is the simplest. All right, and let's keep going, figure out what we're looking for. Pink phenolphthalein, calculate the molar mass of the monoprotic acid. So calculate the molar mass. Okay, so I always want to start with what I'm looking for. I'm just going to put it down here, molar mass of my unknown acid. We know the units for this have got to be, all right, in order to get this, if I had the grams of my acid over the moles of my acid, we're home. We have the answer if we have those two things. So we always want to check, do we have either of those? The answer is yes. We actually already have the 2688 grams that we need. So this question really isn't about molar mass, although we're asking that. It's asking, hey, can you solve for moles of HA? And we do that through a titration. So we do that through a titration saying, look, how much HA? So in order to get, and I know this is a stoichiometry problem because I am starting with the quantity of KOH. Concentration is a conversion factor. I'm starting with a quantity of one chemical, and I'm asking for the quantity of another. So I'm asking for moles of HA, but I'm giving you volume of KOH, and we have those here. So we are always going to start with the volume. So 0.01640 liters times fraction. I want liters to go away. I want moles to remain. This is the concentration of my KOH. So for every 1 liter, I have 0.08133 moles. And this is all of KOH. That's really important to have for this next step. So liters of my KOH solution goes away, and currently I'm left with just moles of KOH. Well, next step, I want moles of KOH to go away, and I want moles of my acid to remain. Ideally, that's what we're looking for. And we know because of my molar ratio, this is a 1-to-1 ratio. Moles of KOH cancel, leaving behind moles of my acid. So if I do the math, 1.334 times 10 to the minus 3 moles of HA. Perfect. So now I can just plug this in. 1.334 times 10 to the negative 3 moles of HA. Do the math, divide those out. You end up with 201.5 grams per mole. Does that number make sense? Yeah, it seems reasonable to find an acid in that region. So 201.5 grams per mole. Perfect. Okay, moving on. So for the next one, it's a little more complicated, especially if you haven't talked about buffers yet, and I'm going to assume you haven't talked about buffers yet. So we're not going to be able to use any buffer terminology for this, but that's totally fine. So here we go. 15 mils of a 0.1 molar cyanic acid is titrated with, okay, so we've done a titration, all right, so something has happened here, is titrated with 0.075 NaOH, and the Ka for cyanic acid is 3.5 times 10 to the minus 4. So calculate the volume of NaOH to reach the equivalence point. Before we do that, we always want to start with a equation. HOCN, which is my acid, plus I'm adding the NaOH as my base. We are left with NaOCN plus water. Okay, so it is a 1-to-1. It looks like it's balanced. We don't have to worry about anything. Volume of my, looks like HOCN is 15 mils. The concentration of my HOCN is 0.10 molar. And my concentration of NaOH is 0.075 molar. Okay, so again, we start with a volume. So 15.0 milliliters of my HOCN. And again, I'm just going to convert that quickly. I'm going to call that 0.0150 liters times fraction. I want milliliters to go away. Actually, sorry, I want liters to go away because I switched it to liters, didn't I? Yep. I want moles of HOCN to remain. So 0.10 moles per 1 liter. This is the concentration of HOCN. All right. Liters of HOCN goes away, leaving behind liters. And what am I looking for again? Calculate the volume. So we're looking for volume. We can do this. Good enough. All right. So times fraction. I want moles of HOCN to go away. And I want moles of my NaOH to remain because I'm trying to figure out how much I need. And it is a 1-to-1 ratio according to this. Moles of HOCN goes away. I've got moles of NaOH left. And then finally, going from moles to volume, we also use concentration. So I want moles of NaOH to go away. And I want moles of I'm sorry, liters of NaOH to remain, NaOH. So the concentration, so this is concentration of NaOH. Concentration is 0.075 moles per 1 liter. Moles of NaOH goes away. I would have much rather used millimoles and milliliters, but I don't want to confuse anyone or kind of send anyone astray. But it's a good thing to use millimoles instead of moles a lot of the time. Do the math, and what you end up with 0.020 liters or 20, give or take. I think I don't know how many sig figs, only 2 sig figs anyway. 20 milliliters of NaOH. All right, so 20 mils is what you end up with as an L, whether you believe it or not. There we go. That's going to bother me. All right, so 20 milliliters of NaOH. Calculate the theoretical pH, and this is where, by the way, having an understanding of buffers is going to be important because this is much simpler with buffers. Calculate the theoretical pH at the 1/2 equivalence point. Okay, so the 1/2. So I know that the equivalence point happens at 20 mils. So the half the equivalence point is going to be when I put in 10 mils, so half the volume. So 1/2 equivalence point equals 10.0 milliliters of NaOH. That's the volume of NaOH that I'm putting in. Okay, so what we have to recognize is the way that this is going to look. If I have my titration curve, okay, this is a monoprotic acid. So we're going to see something like this. That's it. This is the equivalence point. The 1/2 is going to occur right there. That's what we're interested in. 1/2 volume of equivalence when I put 10 mils in. Okay. Another thing, I have all of the acid present here. I'm just going to call it my generic acid, HA. Here, I am going to lose its equivalent. So now I have 100% of my conjugate base. At this point, I should have 50-50 mixture of acid and 50% base. That's going to be really important when it comes to Henderson Hasselbalch, and you probably know what I'm talking about if you've already looked at buffers. So calculate the theoretical pH at the half equivalence point. Okay, so what we really need to do in order to find out pH, I need to know the concentration of my acid at this point. So I need to know the concentration of my acid. So let's do some quick table here just to talk about the idea of it. Volume is changing too. So what I'm going to do is I'm going to think in terms of moles, okay, or millimoles as it works out. So I have this reaction. I have the reaction of my HOCN and NaOH reacting to produce products we're not going to so much care about, but I'll write it out anyway, plus water. We're not going to care about the water. It's just going to, because there's tons present. But this is going to be similar to an ice table, but not quite. But it's going to help us track things. So moles. My initial quantity, well, actually, instead of calling it initial, it's not an ice table. I'm going to call it start. I'm going to start with, so I have 15 mils of zero point 0.1 molar cyanic acid. So if we multiply those out, okay, so 15 times zero point 0.1, not going to do it in millimoles, although my notes are. Well, I guess I can do it in millimoles. All right, anyway. Yeah, so we will do this in millimoles. So we have 1.50 millimoles of HOCN, hydrocyanic acid. At the 1/2 equivalence point, if this were the equivalence point, I would have neutralized, I would have added the equal amount of base, but we're not there. We're at the 1/2 equivalence point. So I am adding 0.75. I'm adding half of the acid that I start with. Okay, so that's what I'm going to start with. We're going to let it run, but that's the idea. I don't have any NaOCN at this point, and I don't really care about the water actually, so I don't need to worry about that. So the change that we're going to see, I am going to lose all of the base. All of the base is going to react because it's the smaller number. Because acids and bases are going to react. The smaller number will completely go away in this case. So I'm going to lose both of these. And I am going to gain a bunch of base along with some water that we don't really care about. So in the end, I should end up with 0.75 millimoles of my acid. Millimoles, that's important. 0 of my base and 0.75 millimoles of my base as well. So at the 1/2 equivalence point, I have half the concentration. We could have done that just from the get-go to say like half the concentration, but that would not have helped because again, I can't just have the concentration because we have to think about the volume. So at this moment, my concentration of HOCN is not half of what it was at the beginning. It's actually half of the moles, 0.75 millimoles, now in 25 total mils of water. Again, I want to reiterate, I started with 15 mils and I added 10 mils for a total of 25. So that's the total volume, current volume, I should say. Okay, so doing that math allows me to finally get a concentration of 0.030 molar. By the way, the concentration of my base is going to be the same exact concentration. Okay. All right. So we now have our concentration of HCN. This would have been so much simpler knowing buffers. You're going to use Henderson-Hasselbalch, and that log term is going to go away. But without that, we can still do it with an ice table. Now an ice table. Okay, so let's set up an ice table as we always do. Anytime we have an equilibrium, two things always get written out. Our equilibrium expression, along with our Ka expression. So products over reactants, H plus OCN minus, concentration of HOCN. It's going to be a little bit different than what we're used to, actually, but initial change equilibrium. I'm interested in the equilibrium number in general. Okay. So again, my concentration that I started with, point again, because of we're at the 1/2 equivalence point, 0.030 molar. But remember, I also have the same amount of base, and let's assume I don't have any acid at this point. I'm going to lose acid. I'm going to gain base, and we are going to assume that that value of x is small, and that these two just can ignore x. And so now I can plug everything because we have the Ka value from above, which is 3.5 times 10 to the minus 4. By the way, this is all leading to something that is going to be very boring and very intuitive in the end. So 0.030 molar, 0.030, it's a 3030 molar. See what's going to happen. X on this side, because these two cancel, 3.5 times 10 to the negative 4. Now, if I know that this is the equal to X, which is equal to concentration of H plus, pH is equal to the negative log of the concentration of H plus. Plug that value in, 3.46. That's it. That's how we solve for it. It's way longer than it should be. When you do buffers, you're going to use the Henderson-Hasselbalch equation. pH is equal to pKa plus log of the how much base you have over how much acid you have. And this is actually just moles. You don't need a concentration, although I'm going to say concentration here. You actually only need the moles. So I'm going to do this really quick. The pKa is the negative log of the Ka, which is 3.5 times 10 to the minus 4, plus log of, so I had 0.75 millimoles of base and 0.75 millimoles, right? Was that our quantity? Yeah, 0.75 millimoles of acid. This turns out to be log of 1. This turns out to be 3.46. What is the log of 1? Turns out to be 0. So I end up with 3.46 anyway. So Henderson-Hasselbalch basically just makes life a lot easier for all points in the titration curve, except for at the beginning and at the equivalence point. So buffers really make this much simpler. But that's how to do it. You can still do it with an ice table. So you don't need to know buffer stuff to understand that. All right, so calculate the pH at the equivalence point. This we cannot use the Henderson-Hasselbalch for. It's not a buffer problem. So at the equivalence point, we have, so all of the 1.50 millimoles of HOCN is now 1.50 millimoles of OCN minus, or the base. So this is the only thing present at equilibrium. And because that's true, I can determine the concentration of my base. Concentration of my base is the millimoles or moles per liter. In this case, millimoles per the total volume, which is another 20 mils, so 15 mils for my original acid solution, and then 20 mils to reach the equivalence point, which we determined in A above. So this is the total volume. Okay. So we know that the concentration of the base is 0.0429 molar OCN minus. Okay, great. This is 100% base. Okay, so what this means is instead of doing a Ka, we're doing a Kb. So the reaction of a base OCN minus reacts with water. It's in equilibrium to produce HOCN, so the conjugate acid, which we started with, plus OH minus. We're going to turn this into an ice table because that's how we do determinations of pH. Molarity, initial change, equilibrium, and we're interested in that equilibrium number. Okay, all right, so we start with my original concentration of point. Oh, before I even do this, I need to do the Ka, but I don't need to do Ka because this is a base, so we need to do Kb. This is a Kb. Kb is concentration products. Again, doesn't matter. OCN doesn't matter what the K value is. It's always products over reactants. So H minus all over OCN minus. We don't write water because it is a liquid. All right, here we go. Now, what is my Kb value? Glad you asked. We do know that Ka of HOCN was 3.5 times 10 to the minus 4. Well, Ka times Kb is equal to Kw. So I know Ka, I'm going to zoom in, 3.5 times 10 to the minus 4. I am looking for Kb, and I know Kw, 1 times 10 to the negative 14. So I can solve for my Kb value, which is 2.87 times 10 to the negative 11. Perfect. So now that I have that, now we can start plugging things in. I know I did this calculation. We have 0.0429 molar. I don't have any, well, I don't care about water. I don't have any of this. I don't have any hydroxide. I'm going to lose my base. I'm going to gain acid. I'm going to gain hydroxide. We're going to assume this is a very small value, which it is. X and X. And now we solve by plugging in our equilibrium values. Off we go. So this becomes X squared all over the initial concentration because we're assuming X is small. And Kb, which we just solved for, 2.87 times 10 to the negative 11th. Solve for X, which is 1.11 times 10 to the negative 6. And now we have to solve for pH. Well, I know my pOH is equal to the negative log of 1.11 times, again, because this is equal to X, which is equal to concentration of OH minus 1.11 times 10 to the negative 6. pOH is equal to 5.95. That number, this is a base, so that number doesn't make sense. Well, it kind of does because it's a pOH, so 14 minus the pH value, or pOH value. Your pH is 8.05. That number does make chemical sense. Oops. That number does make chemical sense. It's basic. It's higher than 7. We expect that to be 8.05. All right, good. All right, last one. Identify the appropriate indicator to use for this titration. So this occurs, it looks like this occurs at 8. So we're going to 8. So let's do 8. There we go. Make sure the line is straight. Just after 8, it looks like a perfect perfect time to use phenolphthalein. If the phenol red looks like it's just before it, and there's a couple others, but it looks like thymol blue becomes green, that one would work just fine too. You're going to use phenolphthalein, and you're going to use phenolphthalein because not being able to see color versus being able to see color is a lot easier than detecting a slight change. Although you're going from orange to green, it, the lack of color to color is just much easier. So phenolphthalein, yet again, so good indicator for that reason alone. All right, that's good. So all of this is going to be posted there, right?